All right, we talked about finding the pH of a strong acid. A strong acid completely ionizes, so to find the pH, you just take the concentration of the acid, and that is your H plus concentration. For a weak acid, we have two sources of H3O plus because there's the acid, but then water itself gives some H3O plus. But we are complicated by the fact that we are at an equilibrium situation instead of completely ionizing. So in order to find the H3O plus concentration for a weak acid, we need to solve an equilibrium problem. So here is an example. Find the pH of a 0.2 molar nitrous acid solution at 25 degrees Celsius. And here is our equilibrium situation. The nitrous acid plus water gives us nitrite plus H3O plus, and the H3O plus is what we need to find our pH. We're given our initial concentration. Our change, we're going to lose some of our reactant and gain some products. So at equilibrium, we're going to have X, X, and 0.2 minus X. Important things to note, water, you notice, does not show up in our table. That's because water is in the liquid phase, and we only calculate for the common phase, so we don't need to worry about water. And the key to solving these is seeing how small the Ka value is, 4.6 times 10 to the minus 4, compared to our initial concentration of 0.2, means that we can use the X is small approximation that we talked about in the last chapter. So our Ka is going to be our concentration of NO2 minus times H3O plus divided by HNO2. And we're going to use the X is small approximation, so we're going to get rid of it there. So our 4.6 times 10 to the minus 4 is equal to X times X divided by 0.2. So then I can easily solve for X, just take my 4.6 times 10 to the minus 4 times 0.2, then take the square root of that. So I find an X value of 9.59 times 10 to the minus 3. If I take that divided by my 0.2, I can see that it is less than 5%. It's about 4.8%. And so my X value is good. The question asked me for the pH. So my pH is going to be the negative log of 9.59 times 10 to the minus 3. So my pH is 2.018 or 2.02. So, all right, let's work through another problem. Again, I would recommend here pausing the video, working it through yourself, making sure you can do this kind of problem. What is the pH of a 0.012 molar solution of nicotinic acid, which is HC6H4NO2? The pKa value is 4.85. So you can see I have a partial ice table here. So again, we're going to lose some X and gain X for my products. The HA and A minus is just, instead of writing all of this out, it's just a generic acid and then its conjugate base. If my pKa is 4.85, That means my Ka is 10 to the minus 4.85, which is 1.413 times 10 to the minus 5. So my 1.413 times 10 to the minus 5 is equal to, I'm going to have x squared from those, and then again we're using our x's small approximation, so it's x squared over 0.012. Sorry, I put an extra 0 in there. And so I can solve for my x. So I get an x value of 4.117 times 10 to the minus 4, which means my pH is 3.39. Now I should make sure that my 4.117 times 10 to the minus 4, my x, is less than 5% of my initial, and yeah, it's 3.4%, so I am all set there. Okay, one more practice question for you. Calculate the pH of vinegar. Vinegar is 5% acetic acid. The density of vinegar is 1.049 grams per milliliter. Its molar mass is 60.05 grams per mole. And the Ka value for acetic acid is 1.8 times 10 to the minus 5. I would highly recommend pausing this video, making sure you can work through this problem. So let's start off by converting our 5% acetic acid into molarity. So we have 5 grams of acetic acid, I'm just going to abbreviate it as HA, per 100 grams of solution. Now we want to convert our grams of our acid over to moles and our grams of solution over to liters. So to go to moles, we know that we have 60.05 grams in 1 mole of HA. Then to convert my grams of solution over to milliliters then liters, I know that I have 1.049 grams of solution in 1 milliliter of solution. And then I know that there are 1,000 milliliters in 1 liter. Let's double check that everything cancels out. So grams of acid, grams of acid, grams of solution, milliliters, milliliters. So I am left in moles of acid per liter, which is molarity. So I can solve that. And I get a molarity of 0.873 molar. So now I can set up my ice table. So I'm going to have my acid, my conjugate base, and my H3O plus, my initial, my change, and equilibrium. After a while, if you're getting used to this, you don't have to keep writing the ice tables for all of these. And then we're going to use the x as small approximation, so I crossed out my minus x, starting with zeros there, x, 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 x. So I'm left with my Ka, 1.8 times 10 to the minus 5 is equal to x squared over 0.873. So my x value is 3.97 times 10 to the minus 3, which means my pH is the negative log of that value, which is 2.40. And I fixed this in your PowerPoint slide 2.4. I got 2.9 when I use more significant figures in my Ka value. If you do it as 1.76, you'll get the 2.9, or 1.76. 1.76 times 10 to the minus 5. Okay, one last topic briefly, polyprotic acids. Some acids have more than one ionizable hydrogen. Those are called polyprotics. And you can, so one acidic hydrogen is monoprotic, 2 is diprotic, 3 is triprotic. And they generally have different acid strengths. Occasionally they're equal, but generally they're different. And each ionizable hydrogen is removed sequentially. So in H2SO4, you remove the first one. It's a strong acid. The second one is harder to remove. So they have different Ka values associated with different hydrogens coming off. The first one, the second one, the third one, etc.